Welcome to Quick MCAT Lessons, where I try to explain MCAT topics in 10 minutes or less. So last time we ended off with electron configuration as basically a map of where electrons are in an atom, what shells, subshells, and orbitals they occupy. They don't fill randomly, they follow a specific set of rules. What are these rules? So we will start with the Aufbau principle. The word Aufbau means building up in German, and that's exactly what this principle says. It says that electrons fill the lowest energy orbitals first and then build up from there. So instead of jumping straight to a higher shell like 3p or 4d, electrons will always start with 1s, then go to 2s, then 2p, and so on, following an energy order, not just the shell number. So the standard filling order up to 4p is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and then etc. So notice how 4s fills before 3d. Even though it's a higher principal energy level, it has a slightly lower energy, so it fills first. Now you don't need to remember this order exactly, you can instead use the n plus L rule. So if you want to know if 6s or 5d will fill up, you get the n and L values for both. So n is 6 and L is 0 for 6s, giving n plus L is equal to 6. And n is 5 and L is 2 for 5d, giving a total value of 7. This shows that 6s has a lower energy and will fill up first. Now to write an electron configuration, you first get the noble gas that preceded the element. So if your element is chlorine, then the noble gas before that is neon. So we would write Ne in brackets. We would then write up to where it is. So chlorine is in 3p. Since neon is at the end of 2p, we would continue from there. So it'd be neon in brackets, then be 3s2, 3p5. Now we say 3s2 because you're just filling up the 3s orbital, and then 3p5. 3p has 6 electrons, but it's not 3p6, it's 3p5 because it's not at the end. It's in the 5th position. You should also note that the lowest S subshell is 1s, the lowest P subshell is 2p, and the lowest D subshell is 3d, the lowest F subshell is 4f. Now we wrote an electron configuration for a neutral element, but it's trickier for a charged ion. Anions gain an electron, so if chlorine was -1, then its configuration would be neon 3s2, 3p6, instead of the 3p5. This is now the same as argon. Now if you have a cation or a positive charge, then the electrons would be removed from the highest n number subshell first. If multiple subshells are tied for highest n value, they would be removed from the highest L value of those. So what is the configuration for iron 3+? To do this, first let's find it for iron. So it'd be argon in brackets, then 4s2, 3d6. Now for iron 3+, the highest n value is the 4s2. So we would remove 2 from here. This would bring it back to what argon is, so you don't need to write anything. But we know that it's now 3s2, 3d6. Now, between 3s and 3d, the higher L value is in 3d, so you'd remove an electron from there. And so this would now be 3d5. And so the correct answer is argon 3d5. And now I tell you it's Fe3+. Now Hunds rule is one of the key rules that guides how electrons fill orbitals within a subshell, like the 2p, 3p, or 3d subshells. The idea is simple, but it's super important. Electrons will occupy empty orbitals first before pairing up. So if you have multiple orbitals with the same energy, these are called the degenerate orbitals. Electrons will spread out one per orbital with the same spin direction before they start doubling up. Think of it like students getting on a school bus. If there are 3 empty seats in a row, each student would rather sit alone than next to someone, unless they have no choice. Electrons behave the same way in degenerate orbitals. So why does this happen? Hunds' rule is really about minimizing electron-electron repulsion and keeping the atom in a lower energy state. So when electrons sit alone in separate orbitals, they're further apart, so they repel each other less. Electrons are negatively charged, so the more they can spread out, the more stable the atom becomes. Also, having parallel spins with the same direction actually leads to a more stable configuration due to something called exchange energy, which is a subtle effect from quantum mechanics. So let's see an actual example, right? Take oxygen again. It has 4 electrons in the 2p subshell, and the p subshell has 3 orbitals. So here's how the electrons go in. The first 3 electrons each go in separate orbitals with the same spin, usually drawn as an upwards arrow. The 4th electron pairs with the opposite spin in one of those orbitals, drawn as a downward arrow. So in the orbital diagram, you would have 3 upwards arrows, and one of those upwards arrows would be coupled with a downward arrow. And just think of this like 3 seats. You have 3 seats, 4 people, right? 2 people are going to have to sit together, and then 2 are going to sit alone. And so this configuration follows all 3 principles. The Aufbau principle, which says lowest energy orbitals first. The Pauli exclusion principle, which says there's maximum 2 electrons per orbital, and they must have opposite spins if they're in the same orbital. And Hunds rule, which says you spread out before pairing. Now in chemistry, stability is everything. Atoms prefer to be the most stable arrangement of electrons possible. 2 configurations that are extra stable, even more than you'd expect just from following normal rules, are half-filled subshells like 3d5 and fully filled subshells like 3d10, and these are especially relevant in d and f orbitals. Now when all orbitals in a subshell are completely filled, for example 3p6 or 3d10, the electrons are paired and perfectly balanced. There is symmetry, minimal repulsion, and high stability. Think of it like a completely full parking garage. Every spot is occupied and there's no extra movement or imbalance. Now half-filled orbitals are also surprisingly stable. They're not as stable as fully filled orbitals, but they're close. Each orbital here has exactly 1 electron, all with parallel spins. This setup maximizes exchange energy, which is a quantum mechanical stabilizing effect that arises when electrons with the same spin can swap places. Here, electrons are as far apart as possible, minimizing repulsion. This is kind of like a classroom where each student has their own desk and nobody's paired up. It's balanced and less chaotic. Common examples of this are chromium and copper. Chromium's electron configuration should be argon, 4s2, 3d4, and copper's should be argon, 4s2, 3d9. And so these move an electron up a subshell, which is unfavorable, but it makes a higher energy subshell more stable, and this outweighs the costs. So chromium goes by argon, 4s1, 3d5, and copper's is argon, 4s1, 3d10. And similar shifts are seen with F subshells, but not with P subshells, as the stability doesn't outweigh the cost there. Now once you understand electron configurations and spin, you can figure out whether an atom is paramagnetic or diamagnetic, and this just tells you how it behaves in a magnetic field. So if the atom is paramagnetic, it's attracted to magnetic fields, and it has 1 or more unpaired electrons. These unpaired electrons have a net magnetic movement because of their spin, which means the atom can be pulled toward a magnetic field. You'll often see this in atoms or ions where subshells are partially filled, especially in p, d, or f orbitals. Example, oxygen has the configuration of 1s2, 2s2, 2p4, and recall that the p subshell has 3 orbitals, which means that there are 2 unpaired electrons, so oxygen is paramagnetic. Diamagnetic is repelled by magnetic fields, so if the atom is diamagnetic, all of its electrons are paired. With no unpaired spins, the magnetic effect cancels out and the atom is actually slightly repelled by a magnetic field. This happens when all orbitals in a subshell are either completely empty or completely filled. So neon has a configuration of 1s2, 2s2, 2p6. All electrons are paired, so it's diamagnetic. That's all for today, and with that we end the first unit on chemistry.